Okay, everybody, welcome back. We're going to delve into topics 4.7 and 4.8, dealing with solar radiation, seasons, Earth's geography, and climate. This is actually one of my favorite uh, groupings of topics to teach. And unfortunately, in this setting, I cannot do it in justice. I could do a whole semester on this stuff. This is really exciting stuff to me. Uh, but we'll see if I can do it some justice as we move through here. All right, so hopefully you guys actually already know this, but I'm going to cover it anyways. What is the difference between weather and climate? Because they are not synonyms. Weather refers to the conditions in the atmosphere at a given place and time. So basically, it's what's going on right now. Is it raining outside? Is it sunny? Is it warm? Is it cold? That's the weather. All right. Climate refers to what it's usually like. So if you were to describe uh, your city where you live in the summertime, what's it usually like in the summertime? You'd be describing the climate. What's it? Typically, it's what you might expect in that area at different times of the year. Hot, dry summers, cold winters, whatever. Okay? So it's more like the average, what it's usually like. And of course, the Earth and different areas have many, many climates. What we're going to look at in this particular slideshow is try to understand what variables are involved with determining what the climate is like in your region. All right. Now, of course, latitude and the intensity of the incoming sunlight is going to have an important role. Two, how close is your area to a large body of water? That refers to a principle we call specific heat that we'll get to. And then topography, proximity to mountain ranges and which direction the wind's coming from influence things like precipitation. So we're going to go through each of those variables as they pertain to climate. All right. So we have to understand what happens to sunlight, first of all, as it enters the atmosphere. Okay, so sunlight enters the atmosphere, some of it's reflected, some of it is absorbed. Okay, so we'll talk about this entering solar radiation. By the way, a really important term for the entering solar radiation is what we call insolation. Not to be confused with insulation that we put like in your homes to keep the heat in or the heat out, right? Insolation is referring to that incoming solar radiation. So one of the basic principles is that whatever energy is coming into our system is eventually leaving it. If we have an imbalance there, we get a system that's warming up over time. By and large, and this is not entirely true, and we'll talk about this in a little bit, but by and large, the amount of incoming solar radiation is equal to the amount that's radiated back to space over time. All right. Um, so there is a little imbalance, but that comes later. All right. So the global average surface temperature is about 15 degrees Celsius, or about 59 degrees Fahrenheit. Um, it is, of course, very, very slowly increasing. But again, that's a global climate change topic for another date. But um, that's the average surface temperature. So if you take day and night uh, and average the temperature over the entire globe, we're going to hover around 59 degrees Fahrenheit or 15 degrees Celsius. Now, of course, where you live, that changes based on the time of year, the time of day, and basic weather patterns. But on any given day, the entire global surface, if you were to average it, it's about 59 degrees or 15 degrees Celsius. All right. Now, as that sunlight hits the atmosphere, right, there's about 31% of it that it's immediately reflected before it really gets very far into the atmosphere to warm anything up. There's scattering effects of little particles in the upper atmosphere. Clouds reflect some of it. The ground directly reflects some of it. All right. Now, the reflectivity of a surface is referred to as that surface's albedo. All right. So albedo is the reflectance of solar energy off the Earth's surface. So about 9% of the incoming solar radiation is directly reflected back to space um, by the Earth's albedo. Okay, now in some locations, We're more than 9%. In some locations, it's less because it's heavily dependent on the color of the surface. So in general, dark colors like forests and the ocean have a relatively low albedo, and that means they have a low reflectivity or higher amount of absorption compared to light colors like the ice caps, which have a high reflectivity and therefore a high albedo. That means areas covered in snow and ice are going to reflect more energy back to space than areas covered with forests or water. So light colors, high reflectivity, high albedo. So the higher the albedo, the less radiation is actually absorbed. So this 9% is an average. All right. Um, Clouds and little particles in the atmosphere reflect some of that. Okay. Now, when we're talking about the absorption of solar energy, right, we get about 69% absorbed. Um, 49 is absorbed by the Earth's surface, 17 by the atmosphere, and gases and dust. Now we'll talk about the greenhouse effect, um, which is a totally normal thing that goes on in the atmosphere. Again, when we get to that climate change later on. But the absorption of that incoming solar radiation means that it absorbs, and those are heated, and then therefore, um, when we feel that warming of a surface or the air throughout the day, that's that absorption of solar radiation that causes that. All right, clouds absorb a little bit as well. Now, it is important to understand that all of this absorbed energy does not stay, right? It all eventually radiates back into space. But the reflected light essentially gets reflected straight back out to space without really causing any warming. The absorbed energy is what warms us up throughout the day, more so in the summer, less so in the winter, etc. Right? But all of that thermal energy that we're experiencing eventually radiates back into space. And that's a good thing because if it didn't, we would just keep getting warmer and warmer and warmer, and we would have an uninhabitable, super hot planet. Okay? So the amount of absorption that we get by the atmosphere, by the ground, by water, right, is essentially equal to the amount that gets radiated back. And so we've reached the sort of equilibrium temperature of the globe of around 59 degrees Fahrenheit. Okay? Now, a reminder of what latitude means. Latitude is referring to the degrees north and south of the equator. So this is our equator right here, right? If we had like a little dot in the center and made angles, right? How many degrees north or south of that equator line are you? That's what that latitude is measuring. Now, that's important because it impacts the intensity of that incoming sunlight. So, at the equator, right? So, if we have incoming solar radiation, the amount in a specific surface area is going to be greater than it would be at the pole. So, we could think of it this way. If we had a flashlight, so if we shine a flashlight straight down, that's sort of like the sunlight hitting the equator, right? 1 unit of light energy heats up 1 unit of surface area. Now, if we go to halfway between the equator and the pole, so for example, Walla Walla, we're right about 45 degrees north, right? That same unit of light, so we're talking about the same amount of insulation, the same amount of energy, right? But it gets spread out over greater surface, and therefore any one point on that surface is receiving less intensity of light, right? And then if we get to 30 degrees, or 60 degrees north and south, so 30 degrees would be that angle. This would be like Alaska, for example. All right, that same amount of light coming from the flashlight gets spread out over two. So they're basically one half the intensity of sunlight at 60 degrees north versus what you get at the equator, which helps us understand, of course, why the equator and equatorial regions are so much warmer than polar regions. And so we want to understand it's not dependent on distance from the sun. That's going to be an ongoing theme when we talk about seasons as well. It's not about the distance of the landmass from the sun. It's because the Earth's like 93 million miles away from the sun. And so the minor change in distance from the sun that you get at different latitudes is insignificant. It's all about the intensity of the sunlight that hits the surface. More intense the equator, less intense, and more spread out or more dispersed the further you get from the equator. All right. Now, how does that impact seasons? So if we were straight up and down, right? So if there is no tilt on our axis of rotation, we would experience essentially one long season that would vary based on latitude almost primarily. Now, because we are tilted, so rather than being straight up and down, we are tilted on our axis, right? That changes the intensity of the sunlight that we receive at different times of year. All right. So in the northern hemisphere summer, which begins in June, right, we're tilted more toward the sun. So rather than getting more dispersed energy, we're getting a slightly more direct rays. All right. Whereas in our winter, that radiation gets spread out over and more dispersed over that surface area. Okay. So again, it's not distance from the sun that causes changes in our seasons. It is changes in the intensity of the sunlight hitting the surface based on the tilt of that Earth's axis. Okay? Um, so in the northern hemisphere, we're tilted toward the sun from March 21st to September 22nd, right? And so our cold season would be opposite. So if we look at the energy distribution at different times of year, what we would experience is in January, most of the heat on Earth would be in the southern hemisphere, which would be their summer, right? And then in July, which is the northern hemisphere summer, most of the heat is distributed to the northern hemisphere, okay? And that's, again, a function of the intensity of sunlight. In the northern hemisphere summer, we're tilted toward the sun on the axis. That creates more direct incoming solar radiation. And in our winter, we're tilted away, which creates a less direct and therefore more dispersed energy. All right. Now, so we talked about latitude as being one of those factors that impact regional climate. Okay. Next, we're going to talk about topography, and then we'll get to a topic called specific heat as it relates to large bodies of water. So let's get to topography next. And this is another important topic here. So topography is referring to the geologic features that we see in a given area. So altitude, of course, is going to impact your climate, right? You all know that higher altitude areas are cooler and receive more snow, etc., often more rain as well. We'll talk about why that is in just a minute. Okay, but the proximity to the mountain ranges is also important, and this is really important here where we live in Walla Walla, Washington. All right. So a rain shadow refers to the impact that mountain ranges have on precipitation. Okay, so some really important vocabulary that is essential for accurately describing rain shadows. Right? We have what is called the windward side of the mountains and what's called the leeward side of the mountains. Now, it would be commonplace to just assume that the side of the mountains closer to water is going to be the wet side of the mountains. And that is not accurate. The wet side is the windward side. Okay. Now, if the wind happens to be blown over a body of water before it reaches the mountains, that adds to the amount of evaporation and probably going to increase precipitation. But the wet side of the mountains is the windward side, not necessarily the side of the mountains closer to water, like a large body of water. Okay, so the wet side referring to precipitation. So in this particular model shown here, the windward side, this would be the wind direction. This would be our prevailing wind. So right here in Washington State, this is a pretty good model to help us understand why Western Washington receives so much more precipitation than Eastern Washington does. So if this was, for example, the Cascade Mountains, right? Um, so the prevailing winds are coming from the west in this particular model. And so as those winds blow over that water, they're forced upward by that geographic feature. Now, we learned in the last lecture that, right, rising air is associated with low pressure and increased precipitation. All right, so we would call that the wet side of the mountains, is the windward side. Okay, now as that air is forced upward, it seeds clouds formation that causes precipitation to fall. Now, as that precipitation leaves the atmosphere, right, that causes there to be less moisture. And as that air is forced up, it cools off, and then sinks on that leeward side, right, we have drier weather. So in Washington State, the west side of the Cascades, which is the windward side, is receives far more precipitation than the east side of the Cascades, which is the leeward side. And it doesn't take very long. So if you drive Interstate 90 from west to east over the mountains, it does not take long to go from a Douglas fir forest to a ponderosa pine forest, which is slightly drier, to no forest at all. Not quite a desert, but pretty arid, semi-arid grassland. Right? And it's simply because of this phenomenon known as the rain shadow. So the windward side is the wet side, the leeward side is the dry side. And again, we want to associate why are we more why do we get more precipitation on the windward side? That's because those mountains cause rising air as the winds blow up over the mountains. Rising air we associate with low pressure, cloud formation, precipitation. The air dries out, cools off, and sinks on the leeward side. Sinking air, higher pressure, less precipitation. All right. Um, so last topic here we want to talk about is like what impact does the ocean and large bodies of water play? Now, ocean currents are going to impact the temperature of the ocean, and that's going to, of course, affect the temperature of the air above the ocean and anywhere near it, right? But another really important phenomenon is what we call specific heat. So specific heat refers to how much energy is required to change the temperature of material, and that's not constant. So for example, water has a relatively high specific heat compared to soil. Okay, so for example, the amount of energy to increase 1 gram of water, 1 degree Celsius, is 4.18 joules, whereas soil, the same mass of soil, 1 gram, right, only requires 1.48 joules of energy to increase that temperature. All right. Now, the reason that's going to be especially important to us is that that means that water heats up or cools off more slowly than land at the same latitude. Okay. So, climatically, the reason that's important is locations near large bodies of water, so oceans or the Great Lakes, right, will have a more moderate climate. That means because they both heat up and cool off more slowly, that means that locations near the coast are generally going to have cooler summers and generally warmer winters. So they won't be as hot in the summer, generally, and they won't be as cool or cold in the winter, generally. It's because that large body of water nearby moderates the change in temperature, right? And likewise, they're generally going to have smaller diurnal changes. So daytime temperatures versus nighttime temperatures, that change in temperature between the peak of day and the dead of night is going to be less than a landlocked area further inland. Okay, so again, let's go back to uh, Western Washington versus Eastern Washington, right? So not only do we have the Cascade Mountains, right, separating us. Let's go back to that rain shadow page, right? not only do we have the Cascade Mountains, but another really important climatic feature here is this large body of water, right? So we would expect a city located on the west side versus a city located on the east side to not only be wetter because of that, because it's on the windward side, we would also expect it to have a more milder climate, cooler summers and warmer winters than a location over here. So again, you could compare Seattle, for example, to a city like Spokane, right? Spokane gets more snow than Seattle because it has colder winters. Okay, partly because Spokane in eastern Washington is not nearly as close to a large body of water, in this case the Puget Sound, as Seattle is, right? Likewise, Spokane is significantly drier overall than Seattle is because Seattle, being on the windward side of the mountains, receives more precipitation than Spokane would on the east side of the mountains. All right, so what we have, right, just in a quick review, latitude impacts the intensity of sunlight, right? Topography impacts things like the rain shadow, also altitude, higher altitudes are colder, okay? But also we have proximity to large bodies of water. If you're closer to a large body of water, you're going to have milder climates, cooler summers, warmer winters than areas in the same latitude that are not near bodies of water. All right.